Okay guys, we're going to talk about chapter 2. Chapter 2 is going to be talking about motion. And when we start talking about motion, we can talk about some differences like how far we've traveled, how far we traveled from our starting point, how fast we're going, our acceleration, and then we're going to talk about Newton's first law. So there's some main things we're going to talk about in this section. But section 1 we're going to describe motion and work on that one. Okay, so when we talk about motion, motion is usually defined as a distance and a time. And so there's always reference points when we talk about motion. An example would be Warner would be a reference point on a map compared to Aberdeen. And so depending on which road you take, depends on how far you have traveled on that and how fast you can travel too. And so that's really what we're looking at, is we're determining based on a reference point our position of an object. So motion can be related to our change from that reference point, and that is what we call displacement. And so when we start talking about displacement and distance, they're completely two different things. Displacement, if I start in Warner and I go to Aberdeen and I come back to Warner, to my original spot where I started, my displacement's 0 because I came back to where I began. However, the distance I traveled, because it's 10 miles to Warner and it's 10 miles back, would be a total of 20 miles. And so there is a difference when we talk about motion with displacement and distance. But the motion of the object depends really on the reference point that you have chosen to refer back to. And so if we look at football, we will use 10 yards. Well, that was the position of the ball. And so the line of scrimmage changes as the position of the ball changes. And so that's also referring to motion and that reference point there. Then we have relative motion. And not all motion is observed as obvious as a car moving. Sometimes it's really slow, such as our planets moving. We don't even notice that we're spinning rapidly out of control. We have no idea that we are moving within a celestial body and it's all just flying by us. So we don't always understand some of that stuff because we just don't see it. And so even if we're not moving, even the molecules in your desk, even though your desk isn't moving, that you can feel, they're in motion. So we always have some type of kinetic energy. Okay, so back to distance and displacement. Okay, so the SI unit for distance is meters. In longer distances, we'll use kilometers. Shorter distances, we'll use centimeters. But it's always that SI unit for meters. And then displacement is the distance and direction of an object. It changes over its starting point. And so again, like we gave that total understanding, if I travel from Aberdeen to Warner, I just stop there, I had a distance of 10 miles and I have a displacement of 10 miles because I'm 10 miles from where I started. However, if I start my driveway at my house, I drive to school and I end up at the end of the day back in my driveway after school, then I have a displacement of 0 because I have now gone to where I have started. And so if you look in your book, on figure 2 on page 39, you see this little guy running. And so if we look at him, he ran from one end line or the start line all the way to the finish, and he ran back. It looks like he's running on a football field. Well, you can see he ran 50 meters down and he ran 30 meters back. Well, his displacement is a total of 20 meters, but his distance he traveled, and I can see I have that wrong on here, so I'm going to change that right now. The distance that he traveled was a total of 80 meters. And so you can see just by looking at that little guy running the difference between displacement and distance. So in your groups right now, I want you to think of some other examples of distance versus displacement, and we'll share those in just a second. Alright, the next thing we're talking about is speed. Speed is the distance an object travels per unit of time. So speed is always going to be measured in meters per second. Distance is obviously meters, time is in seconds. We can also express it in kilometers per hour. However, with the big thing with the SI units, we want to keep that in meters per second, unless we're doing it in longer distances. We don't usually express them in kilometers per second or meters per hour. It's one or the other, and so make sure that when you're doing problems, that if you start in kilometers per hour, it needs to be in kilometers per hour or meters per second, but you can't have it in typically kilometers per second unless you're talking about something extremely fast that's traveling long distances like planetary motion. And so you are going to get a white piece of paper, and you can write everything on this slide on that white piece of paper. Now this is going to be an equation sheet in which you can use for the rest of the semester. And so speed equation is also really important. You can also note this is the same equation for velocity. The only difference between speed and velocity is putting a directional force with it. So speed, you're just traveling at 15 meters per second. But in velocity, you're traveling 15 meters per second north. So you have a direction that's actually going with it. It's just telling the difference between a vector, which has a direction, and a scalar, which does not, which would be speed. Okay, so we are going to look at a motion graph right here. And so when we start talking about this on the x-axis, whenever you're doing a speed graph, time is going to be on your x-axis, distance is going to be on your y-axis. Remember which is going to be your independent variable and your dependent variable. Is it going to be distance or is it going to be time? Right now in your group, I want you to remind yourselves which is going to be the independent variable and which is going to be the dependent variable. You can pause the video while you discuss this. Okay, so now that you know that your independent variable is always on your x-axis and your dependent variable is always on your y-axis, we are going to look at some of this motion. So if we look at the red line right here, you can see that we're traveling at a pretty steady speed and distance, and all of a sudden you hit this plateau mark right here. That plateau mark is actually stationary. The person's actually not moving. And then when we have the decline, they're returning back to that starting position. They could be walking backwards, or they could have just turned around and walked there. Our green line is showing a steady acceleration, and so the distance and time are increasing very steadily and very fast, so they're probably moving at quite a rapid speed. And then we have our blue line here, which has more of a curved angle to it, and that's showing that you're getting faster, but you had some slow moments. It took you a little bit longer to get there. And so these are how we read a speed graph, where it changes in speed. And so we can see that, and you can always graph speed. Now when you're starting to graph this, you'll have different distances versus your time. And so you'll always use a line graph for this. You don't use bar graphs. We also have something that's called an average speed. Basically this is just, well, it's just taking a bunch of different times and dividing it by the total time intervals. And so you can, if you're going 30 miles an hour, 40 miles an hour, 50 miles an hour, you're finding an average speed at which you are traveling to Sioux Falls. However, when we talk about instantaneous speed, this is where we get some of us get in trouble for speeding. Because police officers will take an instantaneous speed. This is a speed at any given point in time. And so when we do an instantaneous speed, if you're going 65 and you have cruise control, and all of a sudden you slow down to 55, and you go back up to 74, well, that instantaneous speed of 74 got you a speeding ticket at the speed limit 65. However, if we look at that, since you went down to 55, 65, and you're back to 74, your average speed would take all three of those and then divide it by 3. And so that's the difference between an average speed and an instantaneous speed. Okay, so again, we're just looking at graphing this. And so on your homework assignment, you're going to be looking at some different graphs and seeing how we can graph motion, and also graphing, determining which ones are people moving in, are they not moving in. And so when we look at this, we want to have again, on the x-axis, our vertical axis, we're going to have time. On our horizontal axis, we'll have our distance. Oh, sorry, I apologize, I said that wrong. On our vertical axis, we have distance. On our horizontal axis, we'll have our time. Each axis will be some type of scale. Now remember, these are going to be in specific increments, and your graph should always take up 75% of your graphable area. So don't make your graphs too small where you can't see them. Alright, so as we talked about earlier, velocity is what we call a vector. It's not only going to have 15 meters per second, but it's going to have a direction with it. So speed and velocity actually have the same equation. Speed is equal to distance divided by time. Velocity is equal to distance divided by time. Again, the difference is that there is a direction added to this motion. And so a cheetah might be traveling at 65 meters per second, but in order for it to be a velocity, we have to say south or north. We have to have some direction that goes with it. If it doesn't have a direction that goes with it, it's not a velocity. So the other thing that we're going to talk about, our last topic that we're going to talk about, is going to be the motion of the Earth's crust. So this is bringing back prior knowledge from last year. So first off, our Earth's crust is constantly moving. And so we move centimeters a year, if not more sometimes. We have these tectonic plates, and these plates sit on top of each other, and they actually will move kind of like an air hockey table is a good way to put it. And so we don't notice the motion because they're moving so slow, but they are moving. The only time we really notice them is when we have a divergent or convergent boundary. Now remember, at a divergent boundary, the continents or plates are coming together, they're coming apart, they're dividing apart, and then at a convergent boundary, they are coming together, colliding. So when we talk about this, we see this at earthquakes. So like in California, where they have lots of faults, we actually will see earthquakes occur. We can feel those, and those are the motion that we feel with the Earth's crust. But we're always in a constant motion. Remember that our continent started as one huge, massive continent called Pangea, and we've kind of moved apart from there, and we're still moving today. And so we kind of see that going. You can also see that in our upper mantle, I apologize, in our upper mantle we will see more motion, but this is what we know as our lithosphere. This is usually rigid rock, and then our anthosphere, or soft rock, is underneath of that. And so depending on where we're at, we get a little bit more motion. But the lithosphere has huge sections, which we know are plates, which can move. Again, these plates are the sites of things like earthquakes and volcanic eruptions. And so like the Pacific Ocean, where we have the Ring of Fire, we have lots of motion in our tectonic plates there, and then like the San Andreas Faults. And then that brings us to a point here. What about South Dakota? Do we have a